We move on to question 11, which reads the following. Here is a cool way to find the square root of a number. Suppose you want to find the square root of 12. You draw a line segment of length 12, and it says here that it is GH in the diagram. Sorry. Yeah, it says it's GH in the diagram. I just wanted to go into this. So in the diagram below, you can see the diagram. So there's GH. G is here and H is here. So this line here is 12 units. Okay. And then it says you extend GH by a length of 1 unit. So it's extended this way. Really should be HG. So FG is 1. All right. So you got GH is 12, FG is 1. Then with the diameter FH, in other words, the extended line, which has got 13 units now, that is the diameter of the circle. So the center of the circle will be, they named it as K, right, which has got radius 6.5, because the whole thing has got 13. You draw a semicircle, right, as you can see. You construct PG, so at this point here, you draw perpendicular to this line here, FH. It cuts that circle which you just drawn at P, right? Then it says that this length, this height, this altitude is square root of 12. So this is a construction, how to construct the square root of 12, right? So then the question is, prove that the construction method works. In other words, what we have just done, right, it gives you the square root of 12, but for finding the square root of any number, in other words, I don't have to take GH to be 12, I can let GH to be any number whatsoever. All right, so let's redraw this. I'm going to draw let's just put this here somewhere, and we're going to draw the line FH. This is going to be the diameter of the circle. So we say that this is F and this is H, and we said that GH now this GH was in that description, it was 12, but now we will say let it be any number n. Let's call it n, right? But FG is 1. And then, if you remember, he drew a perpendicular at G. Oh, I picked the wrong thing here. Let's do it again. Sorry. So drop a perpendicular here. And that thing hits this circle at a point called P. And then the question is PG, let's give a name to it, let's call it H. It's always nice to give symbols to line segments. Okay, then you can do algebra with them. But you have to just keep track of it. But you can keep track in the diagram. So as I've done here now, PG equals H. We want to show that that is equal to the square root of n. All right. Okay, now how do we show it's the square root of n? Let's give a name to the radius. If you draw from the center, let's give a name to that radius. Right? Now we know that the radius is half the diameter. So let's just record that. Your R is half the diameter. The diameter is n plus 1. So it's n plus 1 over 2. Right? Okay, but I'm giving the name R to it. And I think they use the symbol K here. K. Now, you know that Fk okay, so R is equal to this whole thing, this radius here. From the center to the boundary. So this part here is 1. So therefore Gk will be R minus 1. Okay, because the radius, that is a piece, these two add up to R. So this has to be R minus 1. So you have you can use Pythagoras now to calculate. We need to calculate H, but Pythagoras allows us to calculate H squared. H squared is equal to R squared, this hypotenuse, minus R minus 1 all squared. Okay, and you can square the binomial, minus R squared plus 2R minus 1. Or if you want, you can use difference of two squares. So this becomes 2R minus 1. Now, when you look at this, if you multiply on both sides by 2, you get 2R is equal to n plus 1. And 2R minus 1 is actually n. So this is n. And we wanted to find out whether h is the square root of n. H squared is equal to n, so h is indeed equal to the square root of n. So this is a very nice way of constructing the square root of a number. Right? They say using ruler and compass. This with straight lines and circles. All right. So that takes care of that problem. Let's move on to let's just clear out all these drawings first and then get on to the solution. You can see it's exactly the same solution that I've got. Okay. Now we go on to question 12. Question 12 reads the following. You've got a sequence now. The sequence starts from A0, A1. Okay, you guys are at school, you're familiar with first term T1, second term T2, third term, and so on. When you do sequences, arithmetic sequences and geometric sequences, you use that symbol. But in this case here, they are using the symbol A0, but this doesn't represent the first term. A0 is the first term, but the 0, this 1, does not represent the position of the term. All right, but you've got a sequence which is constructed like this. The first term is 2022, and then there's a formula for an plus 1. You can see there's a formula. It's a fraction. It's 1 plus an. That means 1 plus the previous one, right? Because an is the one just before an plus 1. So you add 1 to the previous one, and subtract the previous one from 1, take the quotient, and that is the new term. All right. So there is like a formula for calculating each term in terms of the previous one. All right. So A0 is 2022. Now I'm not going to carry this big number all the way. I'm just going to call it C. I'm not going to call it A0 as well. Let's just call it C. So just remember that C is 2022. Now, according to the rule, A1 is you take the previous one, you add 1 to it, 1 plus C, because we call the previous one C, over 1 minus C. So it's 1 plus previous over 1 minus previous. This is what this says. So that is A1. And A2 is now 1 plus previous. But the previous is this 1 plus C over 1 minus C, all over 1 minus the previous term, which is 1 plus C over 1 minus C. Okay, now that's a rather cumbersome object. The best way to deal with these things is to multiply numerator and denominator by 1 minus C. That kills this denominator. You see, any fraction, you can always multiply it by any number you like. 10, 7. So this is a fraction. So the number I'm going to multiply it by is 1 minus C. So that will flatten this thing here. When you multiply this by 1 minus C, you just get the numerator. So let's just simplify this. I just want to go to the top here. This is A2. I'm going to multiply the numerator by 1 minus C. So you get 1 minus C plus, and the numerator is 1 plus C. When you multiply this by 1 minus C, you're just left with that. The same thing with the bottom. You have to multiply the 1 by 1 minus C. Multiply everything inside. And this is 1 plus C. Right. If you remove the brackets, you have 1 minus C plus 1 minus C. So this just becomes 2. 1 plus 2 is 2, minus C plus C. And you have 1 plus 1. Oh, I'm supposed to have a minus sign here. All right. Sorry about that. So when you remove the brackets, you get minus 1 minus C. So 1 minus 1 cancels. But minus C is minus 2C. So you have 2's cancel. You have -1 over C. All right, now I'm going to keep track of these things as I calculate them. Okay, we had A0 was C. A1 is 1 plus C over 1 minus C. That's A1. And A2, we just worked out to be -1 over C. Right. I need space. So I keep track of it and I can eliminate or delete or erase all these. Let's get on to A3 now. See, the idea is I keep trying to simplify to see whether I'm getting any pattern. So far, I don't have a pattern. I've got C, I've got 1 plus C over 1 minus C, I've got -1 over C. That doesn't seem to have any pattern. So let's continue. Hopefully, we've got A3, A4. This was A3. Now, A0, A1, A2. So I'm working out A3 now. Right. A3 is 1 plus the previous one. And the previous one here is -1 over C over 1 minus the previous one. Now this time I can multiply the numerator and denominator by C. And I get C times 1, C, C minus 1, just the numerator. And you have C, 2 minuses gives you plus 1. Okay. So even here, A3 is, we don't seem to be getting anywhere yet. Okay, so let's try to work out the next one. I've got A3, so I can calculate A4. Each one can be worked out in terms of the previous one. So you got A4 is equal to, now you got C minus 1. So it's 1 plus C minus 1 over C plus 1. That's the previous one, over 1 minus C minus 1 over C plus 1. So once again, you multiply the numerator and denominator by C plus 1 plus, let's put this in brackets, because if there's a minus sign in front, then you have to change the signs. So I have to multiply this, the denominator by C plus 1 minus, we put a bracket around this, the minus changes the sign. And at the top, I got 1 minus 1, which is 0. C plus C is 2C. Denominator, you got C minus C is 0. 1 plus 1 is 2. Now we've come back to the starting point, you see? See, you come back to the starting point. So this means that if I proceed, I'm going to have the same thing repeated. See? A0, A1, A2, A3, A4. Now I'm going to do what I've done there to get to this. So this is A5, A6, A7, right? A8, right? Is C, and then you continue. So the sequence, I think I'm just going to write it down like that. I've got A0. I've got records. This is A0, remember, A1, and so on. A0, A1, A2, A3, A0, A1, A2, A3. A4 is the same as A0. A4 is the same as A0. So now you'll carry on. A1, A2, A3, A4. A4 is A0 again. All right. So now it's predictable. You needed to calculate, we didn't look at this question, what is the value of A 2022? Okay, I can see there are four of them, right? So they come out in groups of four. I'd like to think of this one here. You see, A3 is occupying the fourth position, right? Because it's groups of four, worry about the fourth position. The fourth, eighth, right? And so on, 12th. And now these are all multiples of four. That's why I chose this, because the nearest multiple of four, we need to get to the neighborhood of this point here. And that we can see the nearest multiple is 2020. 20th terms are all equal to A3. Right. So you got that. So the 2020th term is therefore A3. So this is A 2020. Right? And this is equal to A3. So the next one will be the one after A3 is A0, 2021. And we are interested in 2022. After A3, you get A0. After A0, you get A1. So the 2022nd term is actually A1. Um, A3 was A0, A1, A2. A3 was C, isn't it? No, A0, A1, A2 is minus 1 over C. This is A3. And A4 was the same as A0. Yeah. No, this is A5. A0, A1, A2, A0, A1, A2, A3 minus A4. Right. So A4 is A0. Right. So you have fourth, eighth. I'm sorry. This is not the answer that I got, that I remember. So the 2022 22nd term is A1, and A0 is this, A1 is that. And then you can put C equal to 2022. Now this is wrong. 1 minus 2022. I'm not sure what happened here. Let me just look at my solution, if you don't mind. I got A3 is C minus 1 over C plus 1. A0, A1. Right, that's okay. I got C minus 1 over C plus 1. And I have A4 is A0, A0, A1, A2, A3, A4. That's the same as A0. It's not A, yeah, okay, it's A0. Oh, I know. Yeah, so what happened was, the problem is that it starts from 0, you see. So that is why I have a problem. Okay. So let's just clear out all this. And if you look at my solution, you'll see I've got the fourth 12th term is all A3, as I said. So the 2020th term is A3, right? That's right. And the 2022nd, right? The 20th is A1. And A1 is minus 1 over C. Right. I was looking at this one here, but this is really A1. Right? 20th. This is the 2020, 2021, 2022 will be A1. And A1 is A2. All right. Okay, so you can read this and you can see the answer is really -1 over 2022. Because I'm starting from A0, that confused the matter a little bit. But just think about that. Okay, let's get on to the next problem. The solution is yes, so you don't have to worry too much about this. You can have a look at that. But most of the problem is, this is how you calculate these problems. You use the formula to work out each term, one after the other. All right, let's get on to the next question, which is question 13. Question 13 says the following. A two-digit number is divided by the sum of its digits. Right. So let's just see what this means. If I take a two-digit number like, it's like 23, that's a two-digit number. And I divide it by the sum of its digits, 2 plus 3. So I'm dividing 23 by 5, right? What is the largest possible remainder? And here the remainder is 3, because this is equal to 4, remainder 3. Now you got a lot of two-digit numbers, all the way from 10, 11, 12, going all the way up to 99. And you want the remainder to be as large as possible. What is the largest possible remainder? Now remember, the remainder is always is it'll be smaller than the denominator, right? So if you want the remainder to be as large as possible, then you must make the denominator large, because the remainder will be now coming from a larger set. All right. So if you want the denominator to be large, then we have to start from the largest. The denominator is the sum of the two digits. So if you got a two-digit number, 10a plus b, that's how we write a two-digit number. You want a plus b, right? So you want a plus b to be large, to get a large remainder. The remainder is always smaller than the denominator, right? Okay, so let's start from 99. I've got the diagram here to make life easy. So we start at 99. The digit sum is 18, 9 plus 9. Divide 99 by 18. 18 times 5 is 90. So the remainder is 9. Okay, so the remainder can be 9. And now you want to get the largest possible remainder. So you must try to see whether you can get something which is larger than 9. Let's take the next one, 98. 9 plus 8 is 17. The 17 goes into this 85, remainder 13. And that's quite a large number. Right. Now, what this means is that your denominator, to beat this one, I need to get a larger remainder. I need to have the denominator be at least 14, right? That means the sum of the digits must be at least 14. I can take 97, I can take 96, I can take 95, but I have to stop there. The 94 will be 13, and the remainder will be smaller than 13. So let's try to see whether we can get, yeah, it's 9 plus 7 is 16. We are hoping to get the remainder 14 or 15 to beat this one. But then when you see the remainder, you see the remainder is 1. And 96 is 15. 15 goes into 96 6 times. 15 times 6 is 90. The remainder is 6. Still no dice. 9 plus 5 is 14. 14 goes into this 84. The remainder is 11. So we haven't beaten 13 yet. So far, this is the best candidate. The largest remainder is 13. Okay, now remember we came to stop to 14. We now must make the numbers here, the sum must be more than, not even 14, because 14 will give you the largest remainder when you're dividing by 14 is 13. I don't want to equal this. I want it to be bigger. So I want to take numbers which are with digit sum is 15 or more. So now let's go to the 81s. 87 is 15, 88, 89. Right? These give you the digit sums 15, 16, and 17. Right? And when you divide 87 by 15, the remainder is 12. When you divide 88 by 16, the remainder is 8. You can try it. 89 by 17, the remainder is 4. So still, this is the top dog, 13. Okay, now this is where you stop because you can't get a larger sum than 17. Let's try. We need to get the remainder, the sum of the digits to be 15 or more. In the 78 case, it's 78, 79. Those are the only ones which are 15 or more. Here it's 15. 78 goes into 15. 5 times the remainder is 3. and here it's 16, and 16 goes to 79. 4. 16 times 4 is 64, and the remainder is 15. Ah, we have beaten it. We have beaten it. Okay. Now, I say we're going to stop there because now you want the sum of the digits to be 17 or more, right? To get the remainder larger than 15. But now, when you go all the way up from 10 to 69, and you add the digits, you can't get the largest possible sum you will get is a 69, and that is 15. And all the other sums are smaller than 15, right? 59 is 14, 49 is 13, and it becomes smaller. So there's no point in trying any of the previous ones, right? And you can stop right here because you're not going to get a remainder larger than 15. Okay, so the answer to the question, right, the largest possible remainder occurs at 79. Right? 7 plus 9 is 16, and the remainder is 15. So that's the answer. Interesting that number 79 is playing that role amongst the two-digit numbers. Okay, so let's just clear out all the drawings, and you can have a look at the solution that I had worked out. You can see at the bottom there you got 15, the same diagram which I had, and that ST means stop. ST means stop here because there's no need to. I explained why you have to stop there, because all the other numbers, the digit sum is less than, is 15 or less, in which case the remainder will be 14 or less. It's not going to beat 15. All right, so let's get on to the next problem. Question 14. Okay, oh, somebody's birthday here. You want to divide a birthday cake in a non-traditional way. The area of BDF. All right, so there's your birthday cake just for glamour to do the diagram. And there's the top of the cake. And this is a cut here. You're cutting out a piece like that. But now you want to draw a circular cut at the top. I don't know what kind of instrument you would use to cut this thing, to cut it right through, but whatever it is, mathematicians, they set all kinds of problems. Okay, you got a circular cut like this, and it says the area of BDE, this area, BDE, let's call it X, is the same as the area DACE. DACE. So this area here is also X. Okay. And the question is, what is the ratio of AD to BD? Okay, let me just create some space here to do my writing. So AD to BD. So we let, okay, now what I'm going to do is, you see, I've got BD and I've got an area, a partial area of a circle, right? And BD is the radius of the circle. So let me give a name to BD. I'm going to call it A. So BD is A. And the other radius, the larger radius, as I said earlier on, I like to use symbols for these lengths, even for areas, so you can do some algebra. So what we've got here is, this part here is A, and this whole thing is B. Okay. Now, let me just wipe out these two x's. I'll have to remember that those two areas are the same. Okay. Now, I can calculate areas. You see, this area of BDE let's call that x also. Now, the area of BDE is a piece of a circle. And what you've got here is, go up to the center, and you've got the radius. Is A. Now, what's the area? It all depends on this angle. See, if this angle was 90 degrees, then the area is, it's going to be a fraction of the area of the circle. So the area of the circle is pi a squared, right? And this thing here is going to be a fraction of the area of the circle, but the full angle is 300. You see, if it was 90 degrees, you'll say it's quarter. Why? Because 90 over 360 is a quarter. If this was a straight line, you'll say it's a half. Why? Because 180 degrees is half of 360. So really what you're doing, you're looking at the fraction, theta over 360. Right? This fraction of 360 times the area of the whole circle is this x that we're looking for. So this is theta over 360. We'd better give a name to this angle between these two. Right? Theta over 360 times pi a squared. Right? It's that fraction of the small area. And likewise, the area of BAC. And here we are looking at this entire piece of the pie, of the birthday cake. And that'll be something like, it's a similar kind of a thing. And let's call that Y. This is Y, this whole shaded area. And that area, again, it's the same fraction because it's the same angle. But now it's the area of the large circle, which is pi b squared. Okay, so you have a nice equation. There, like that. So we can say x over y. See, much easier to use that rather than this cumbersome thing. X over y. Just remember, x is the area of this top piece. I'll come back to that. Why do I say x over y? Because I can cancel a lot of things here. This cancels, theta 360, pi's cancel, and you see that you get a squared over b squared. Right. Now, let's just keep track here. AD is to BD. What do we need to calculate? Let me take out all the stuff. And you got AD. Now we said that BD is A, and AD now, the whole thing is B. The BA is A. So AD is to BD, well, it's a fraction. You can put AD over BT. Same thing as that, right? Now what is AD? AD, the whole thing is B, and BD is A, so you have to subtract. It's B minus A, whole radius minus the small radius is AD, and BD is, so this is what we need to calculate. Right, so we're getting there somewhere because we got A squared over B squared. Now we haven't used the fact that we said that this is X. And we said the whole thing is Y, this whole area. So this piece here is Y minus X. Because when you add X to that, you're going to get the larger piece of the cake. But we are told that this Y minus X is equal to X. We are told that this area here is the same as that area. So we have a nice equation. Y is equal to 2X. But if I put Y equal to 2X, this thing simplifies to X over 2X, because Y is 2X. You get a nice answer. It's a half. Okay, so you got that A squared over B squared is a half. Right? Knowing that, now we need to calculate that object there. Okay, but now you can actually, if A squared over B squared is a half, then A over B will be 1 over the square root of 2. The square root of 1 over the square root of 2. Now we want B minus A over A. And that's what we need to calculate. This is B over A minus A over A. Right? B over A minus A over A. Now B over A, there it is. 1 over A over B is 1 over root 2. So B over A is root 2 minus 1. You just have to invert the fraction. So that's the answer to the question. This is equal to root 2 minus 1. Or if you want to really answer the question, is AD is to BD is root 2 minus 1 is to 1. So this is, the denominator is 1. Okay, so the lesson from here is that using symbols, you can do a lot of algebra, but just remember, you have to keep track of what your symbols mean. That's the most important thing. X was the area of that, and Y was the area of that. So that is why we could create some equations. All right, so the next problem, let's just clear all these diagrams and see whether so there's the answer. It's exactly the same as what I did. And you will see I got root 2 minus 1. I even use the same symbols. Excuse me. Now we go to question 15. Question 15 is evidently a geometry sum. So what does it say? 4 squares are drawn below. Okay, just bear in mind, all these are squares. They're not any rectangles, they are squares. The area of the bottom left square is 4 units. Okay, if the area is 4, then at least we can give a start to that. It means that the side is 2. Okay, so let's just proceed from there. Even this side is 2, but this other thing is a square also. So if one side is 2, all the sides are 2. Okay, so this is another square here. But now this length here is 4, right? And it's the side of the second square, right? So the side of the second square is 4. So all the sides are 4. So you got that is going to be 4. But this one here, you don't know what this length is. Because you can draw any square here, quite large. It looks as if there might not be an answer to this question. Determine the area of the shaded triangle. The shaded triangle, it's got one of the sides is the diagonal of the small square. And you've got the other vertex is sitting at that corner. Okay, so how do you solve this problem? The geometry problem, there's a lot of intuition, and that's why people are scared of geometry, because you have to use um, your intelligence to try to see whether you can solve the problem. Now remember, you got a diagonal of a square. A diagonal of a square is very has got the property that it bisects the opposite angles. Any diagonal of a square, it's the angles at the it divides the opposite angles equally, 45, 45. Right? There are lots of properties of a square, but this is one of them. So it makes 45 degrees. Okay. Now, what I want to do is I'm going to draw the other two diagonals. Especially this diagonal here. Because the vertex of this triangle is sitting on this line here. And this line, I've got a feeling that is parallel to this. Okay, let's see whether that is true. Well, this is the diagonal of another square. Let's write down these of 45, 45. Okay, now is it parallel to this? You got this little angle here, but we don't know what that angle is. So how do we know whether it's parallel? Why don't I join this other diagonal here? This diagonal of the square. Might be able to get something out of that. Well, once you draw that, then you got, again, you got the 45 degrees scenario. You got that this is 45 degrees, 45. And here too, you got 45, 45. Oh, this diagonal here is also 45 here. So I've got all three diagonals, all three squares, I've got a diagonal drawn. Now, if that is 45 and this is 45, this means that this angle here is 90. From here to here. But this from here to here is also 90. But these are alternate angles, right? You see, this diagonal coming down, going up, alternate angles are equal. Both of them are equal to 90 degrees. So these two lines are actually parallel. Actually, I've got this diagram is too cluttered. Let me clear everything out. Okay, and just worry about the main things. we found that this line here is parallel. That's what I've just shown to this one. Now, this is a very, very helpful thing because you've got a triangle here whose base is this, and you got it's sitting between two parallel lines. Now, this is a very well-known fact that if you've got two parallel lines, and you got triangles having the same base, then all these triangles have the same area, the ones that I'm drawing. Because the formula for the area of a triangle is half base times height, and all these triangles have got the same base, and obviously got the same height because they are between the same two parallel lines. The height would be the distance between these two parallel lines. So this area that we're looking for has got the same area as this one. The area of the triangle whose base is that. See, it's a little bit tricky, difficult to see, but the parallel lines, and that point and this point are on that parallel line. So this is the same base. So what we're looking for is the area of the rectangle. The required area equals the area of the red triangle. Because the red triangle has got the same base and the same height as the shaded triangle, whose area we were trying to calculate. But the red triangle is easy because the one base is, you see, remember this is 45, this is 45. So the red triangle is the right angle triangle. Right? And let me just make this a little bit neat here. And so this is a right angle triangle because you got 45, 45. So we need to calculate the base and the height. Now, remember we said that this was 2. And that is 2. And this is the diagonal. So the base is half base. And I think I mentioned earlier on that if you got two isosceles triangle, this is the square root, the hypotenuse is 2 times square root of 2. So the base is 2 times square root of 2. That's the base of this. And the height is that one. And that is the diagonal of the square here, which has got side 4. So it will be 4 times square root of 2. See, whenever you got a square, and you know a side, the diagonal is very immediate. This is S, this is S, then the diagonal of that square can be calculated immediately. Because by Pythagoras, it's square root of S squared plus S squared, which is square root of 2S squared. and the square root of 2s squared, you can take s out, s root 2. So in other words, all you have to do is to take the side and multiply by root 2. Here the side is 4. Oh, this one here, the side is 4. So this is 4 root 2. So the diagonal is 4 root 2. That's why, that is how I got 4 root 2 here. Okay. And now this is easy to calculate. Root 2 times root 2 is 2. 2 divided by 2 is cancels off. And the only thing that are remaining is 2 and 4. The answer is 8. 2 times 4. Okay. Interesting problem, because it doesn't matter how big the square is, you'll always get the same area. It's quite intriguing, where you can draw a very large square like that. But that area will also be 8, even if it's so far away. Okay, so that takes care of problem 15. And yeah, normally there are 15 questions, but I don't know, these people decided to give 16 questions. I don't know why they do that. As it is, this thing takes a long, long time to calculate, to work out. You need to have, there was no need to increase the number of questions. Okay, let's get to the last question. That is the 16th question. Okay, here you have a cylinder with diameter root 2. Okay, we're given the diameter is square root of 2. Just bear in mind the diameter of the cylinder is square root of 2. A square hole with side length 1 is cut through the center. So here you've got, there's your circle, and you cut a hole, but it's a square hole. You cut right through the center. So that the square tube fits exactly into the tube as shown. So you got the square tube here, it goes inside. See, once you create the hole, then the space inside, actually the hole is here, right? And now you are thrusting this square tube. It doesn't look like a tube, it looks like more like a rectangular cylinder. Anyway, that fits in exactly inside here. Now they say determine the volume of the part that was removed from the cylinder. In other words, this part here, I just want to show you something. This is quite revealing here. You see, there's a hole which is created here, and this thing, it fits exactly into that. But you'll notice here, slight thing, you got a line there, and this part here is curved. So the base of this is a curved, it's part of the cylinder, and the other part is also curved, but you've got a straight line here. So the base consists of two parallel straight lines, and you've got two other pieces which are circular. Now that's what I've drawn here. The green part. This green part represents the base of the removed part. So let me just keep record of that. This green equals base of removed portion. So if you look at the base, you'll see two edges are straight. That's what I've got. But then there are two edges which are curved, and these curved edges are part of a circle, whose diameter, by the way, is square root of 2. If you take any cross section of the circle, you're going to get the same diameter. It's given that the diameter is equal to the square root of 2. Okay, now you need to calculate the volume of this object here. Okay, the volume of any vertical object, no matter what you have at the bottom, as long as it's vertical, it's solid, you got exactly the same thing at the top. The volume of this is always the area of the base times the height. So if I had a cube, for instance, whose sides are A, B, and C, then the volume of the cube is the product of the three sides. It's really the base, area of the base, which is a square, AB times the height. So it's AB times C. But even if you have a circle like this, the volume of the cylinder here is area of the base, which is the area of the circle, times the height. In this case, you've got this base here, so it's the volume of that cutout piece is equal to green area. That's the area of the base times the height. Now the height of this, it says that this square hole, this thing fits exactly. So in other words, the height is exactly equal to the height of this thing. But this is square 1 by 1 all around. So the height is, that is the height. That is going to be equal to 1. Okay, so the volume is actually the green area. So I need to calculate the green area. Okay, now how do I do that? So I need to calculate the green area. I've taken everything out because I know where I'm heading. Now let's see, the green area, it's made up of let's break it up like that. Now remember, this is a square here because you got a square hole, right? So this inside part is a square, and you need to calculate the area of the green part. We also know the diameter. Now we know the diameter is square root of 2, but as I told you many times, I don't like to carry all these square root of 2 and all that. We'll just call it A, and bear in mind 2A is equal to square root of 2. Later on, we'll make the substitution. It's necessary. Okay, now I know the diameter of this. So I should be able to calculate the green area. Let's divide the square up into pieces like that. Then the green area consists of, okay, let's call this capital A. All these are the same. And this part here is also the same. So the volume is equal to the green area, which is 4A plus 2B. I divided up this green area into several pieces, 6 pieces actually. You see, the problem is I've got the small piece of the circle there, and that is not easy to calculate, right? But as we saw earlier on when we did the pizza thing, I can calculate a plus b. A plus b is just this angle is 90 degrees, you see. The diagonals of a square bisect each other at 90 degrees. See, again, we use the properties of a square several times. These angles are equal, the diagonals are equal, the diagonals bisect each other, and they all meet at right angles. So you've got that. So this pizza pie is just a quarter of the area of the whole circle. So a plus b is actually a quarter of the area of the whole circle, and the circle has got radius a, so the area of the circle is pi a squared. So that's a plus b. Now I want 4a plus 2b. So the volume, why don't I just separate it? It's 2a plus 2a plus 2b. Because I know a plus b, you see. So it's 2a plus 2 into a plus b. Now what is 2a? Now 2a is just half the area of the square. And this is a plus a. And the area of the square is a squared. No. The area of the square is or let's call it b. So the area of the square is twice a, which is half b squared. The area is side squared. And this is 2 times a plus b, which we saw was a quarter. So 2 times quarter is pi a squared. Now b squared is b squared plus b squared is 4a squared, because you've got this right angle triangle outside. So b squared plus b squared, sum of two sides of the squares of the two sides of the triangle. Hypotenuse is 2a, so it's 4a squared. Okay. All right, now we are nearly there. I can put everything in terms of a. So b squared is 2a squared. Right, so if b squared is 2a squared, half b squared is a squared. So I can replace this half b squared by half of 2a squared, which is a squared. Now I'm there because a is this. So what is a squared? This implies that 4a squared is equal to 2, squaring on both sides. So a squared is half. Fine. I got a squared on both places here. So a squared is a half plus half. Pi a squared is a half. So it's pi over 2. So you have a half plus pi over 4. See, when you use symbols, everything works out so neatly. But you have to keep track. See, you put a symbol like this, then you must see what equation you can get out of that. And so you notice I've got no square roots anywhere because I've used symbols and took squares rather than taking square roots. Okay, so the answer to this question is a half plus pi over 4. Oh, there we go. You can see right at the bottom, half plus pi over 4. All right, so that brings us to the end of this paper, 2022 Junior Round 3. As you can see, the Round 3 problems are quite challenging. But if you do enough problems, and you've got a lot of problems now which have been solved, if you do enough work and work on your own and try to solve the problems and look at the solutions that are given, I did all the junior round threes all the way from 2019, I think, up to 2025. So you got 7 uh, papers to go through, and you learn quite a lot if you go and listen to all the video tapes of that. Okay. So thank you very much for listening. And we now end this session.